in this lesson we're going to be looking at the rest of the reactions as well as condensation polymers and reaction schemes. So now you can see this clearly with the reactions we've done so far in the previous lessons. We first looked at the alkenes, and we had hydration, we had halogenation, and it can be used for Cl2, but if it's Br2, then it's the test when it decolorizes the brown, orange-brown bromine. Then we've got the hydration, which is the conch sulfuric acid and water to form an alcohol. Then we have the hydrohalogenation, which is HBr, HCl to form the haloalkane. And then we also have the other test where it decolorizes permanganate, and if it's acidified permanganate, it turns it from a purple color to colorless. And then we form a diol, so we have a OH added onto each carbon of the double bond. Then we looked at the haloalkanes, and the first reaction we looked at is making the alkene again, and then we applied Zaitsev's rule for major and minor products, and remember we had alcoholic OH minus, and also heat to push that reaction to eliminate it. We also looked at hydration, which was a substitution reaction. So I've done the types of reactions in all the different colors here, and that's where we use aqueous OH. Compare that to the alcoholic OH. Okay, don't get muddled between them. Then we had other substitution reactions. The first one was hydration. The next one was adding conch ammonia, and that formed a primary amine, or I could react it with a primary amine to form a secondary amine. So those were the four reactions of the haloalkanes. Then we looked at the alcohols, and we had again forming the alkene, and it was in concentrated conditions forming an alkene. We again apply Zaitsev's rule. We also then had forming an alcohol, going from an alcohol to form a haloalkane. And remember I said SOCl2 is the good one there. I put these in here, HBr, HCl, but actually you also should know PCl3 or PCl5 as well. They're from last year. They may come up, but I doubt it, but just bear it in the back of your mind. Then we also had, so we had elimination for alcohols, we had substitution for alcohols, and then we also had oxidation, either oxidation of a primary alcohol to an aldehyde, or oxidation of a secondary alcohol to a ketone. Or we could oxidize it further, a primary alcohol, to form a carboxylic acid. So we've got 13 reactions that you've learned so far, okay? And then we can also reduce an aldehyde to a primary alcohol, or the aldehyde can be oxidized to a carboxylic acid. So aldehyde can either go up or it can go down. Ketones can only go up to form an alcohol. They can only be reduced. They can't be oxidized further, because remember I said there wasn't that hydrogen attached to the carbonyl that could be removed. And then after we did the alcohols, we looked at the amines, and pretty much with the amines we had two reactions. One was the acid base, so it could react with an acid to form an alkyl ammonium salt, and it can be a primary amine that does this, or a secondary amine, or a tertiary amine. They can all do this. The other reaction I've already done, which is a primary amine with a haloalkane to form a secondary amine. This is the reaction we're going to be doing today. So you've learned 15 reactions so far. So you've done a good lot. And then the tests you need to know is the bromine, the permanganate, that's for the alkene. And then we've got two tests for the aldehyde, which is the Tollens and the Fehlings. Remember, Tollens is a silver mirror test, and the Fehlings is when that blue copper sulfate solution goes and becomes that brick red copper 1 ion color. And the other tests you could use is the dichromate changing color. The alcohol can change the color of dichromate to form an aldehyde or a ketone, depending on what we've got, or an aldehyde can change the color of dichromate to change it from that orange dichromate to green chromium when it forms a carboxylic acid. You could do the same with permanganate as well, when acidified permanganate decolorizes. Have you got any questions on the reactions so far? No. The hardest part is learning them, and as I say, flashcards or learn a reaction per day. That organomy thing is just fun ways of trying to make you look at those reaction conditions and so on. Right, so what we're going to look at now is carboxylic acids and their derivatives. So looking at carboxylic acids, again, it can react in a number of ways like alcohols, because we have two reactive centers. The first one is the carbon, and the carbon is slightly positive because it's got two oxygens withdrawing electron density from it, because oxygen is more electronegative than carbon. So what sort of thing is going to attack a carbon in a carboxylic group? It's something that's electron rich. Yeah. So it's not electrons themselves, but it'll be nucleophiles. Electrophile is something that loves electrons, so it has to be positive itself to love electrons. An electrophile will repel electrons. An electrophile has to be positive to attract electrons. If it was negative, it would repel electrons. So it's a nucleophile. So something that's electron rich is actually a nucleophile because it has to be negative to attract the positive center like that carbon. Does that make sense? So if something is positive, it gets attacked by nucleophiles. Philes means Philio, Philip, lover of horses. Okay, it just comes from that Greek word. It means, so nucleophile, positive, loving. Okay, the other part that reacts with a carboxylic acid is the hydrogen. This bond is very polarized, so the hydrogen can get lost quite easily. And so, you know, vinegar is acidic because it can donate a proton. So those are the two reactions affected by nucleophiles, so it's substitution reactions, or it's acidic. And there they are. So substitution, the OH is replaced by an incoming nucleophile, and the other one is acid base, where that hydrogen is donated to a base. And one thing I didn't show here with these, what happens when it's substituted, this whole OH group comes off, including those hydrogens. When it's a proton being donated, remember it's just the H, the electrons in the bond stay with the oxygen, they don't go off. Okay, so here we're going to see those two types of reactions. There's ethanoic acid, and I've tried to show that carbonyl-carbon is pretty positive because it's got electron density being withdrawn, and the hydrogen is fairly positive as well. So if I add conc ammonia, the ammonia can act as a nucleophile, so it's attacking that positive center, and I form what is this compound called? If you like, just give the functional group, or you can give the whole, yes, it's an amide. Okay. I could also use ammonia and use it as a base. And, sorry, I forgot to say, the leaving group is water, because, can you see, it's this OH group that comes off, plus one of the hydrogens. Ammonia had 3 hydrogens, there it's only got 2. So I've got a nice neutral leaving group, so this reaction happens quite readily. So there's ammonia acting as a nucleophile. It's electron rich, so it's attacking something that's electron poor, and it's replacing that OH. It can also act as a base. So what is a base? It's a proton acceptor, and so it's accepting that proton. So can you see it's got that extra proton and it's removed it from the carboxylic acid. So that's now an anion, and this is a cation. So very concentrated conditions, it tends to be a nucleophile. Slightly more dilute conditions, it tends to act more as a base. Right, So what we've got in this one is, just because you might be asked to, how would you know something is a carboxylic acid? And the obvious test is test it as an acid, and so if it gives off carbon dioxide when it reacts with a carbonate. So that's what they're showing as a carbonate there. And I'll just move it on a bit to around about here. He's now going to add it in. I see you typing there. Now he's adding the carbonate in. It's an old test, yes, but it's a goodie and it's a good one. Now you can't really see the bubbles over there. It wasn't that well shown there, but there are the bubbles, and he's going to show now a lighted splint. The flame went out because carbon dioxide doesn't support combustion. So it's a good one to know. Here's this thing about increasing reactivity when I go from all the derivatives, and why there's this change in reactivity. It's because of my leaving group that comes off. So all of these can undergo substitution reactions because the carbon is slightly positive in each case. But if I look at what is coming off, in the first case with the acyl chloride, I've got chloride coming off. Now, is that strongly acidic, strongly basic, or neutral? A chloride. A chloride's actually neutral. Okay, it's the anion of a strong acid. It is totally neutral. pH will be 7. So sodium chloride, for instance, the chloride will be just neutral. Oh, okay, yeah. So the chloride, I mean, obviously HCl is acidic, and chloride is the conjugate base, but really the pH is 7 for chloride. So that is neutral. It comes off easily. It won't act as a nucleophile and attack back again very easily. Here, if I break this over here and this OH comes off, it comes off with electrons, OH minus, and you know that's a hydroxide. It's a strong base. If I have a ester, then if it gets broken over here with the OR, or like if that was a CH3 group, it would come off then as a methoxide because it's taking the electrons. Methoxide or any alkoxide is a really strong base, so of course it'll be also a really good nucleophile and straight back on again. And then of course you've got the NH2. If it comes off with the electrons, it's NH2 minus, and that's an even stronger base, so it'll act even as a stronger nucleophile. So because this NH2 doesn't come off very easily because it's so strong, an amide is not as reactive as an acyl chloride. So this is the most reactive going to the least reactive, just because of the leaving group getting more and more basic. And that means whenever you're trying to do a reaction, it's always good to go and form the acyl chloride first and then carry on a reaction, because these won't react very readily further. So if I'm trying to make something, go to the acyl chloride and then react the acyl chloride. Now, I've got here what is the leaving group in neutral solutions, acidic solutions, and basic solutions, because these all actually have a weak link in that the leaving group changes when I change into acidic or basic solution. So our acyl chloride always has chloride as a leaving group. So there's no change. And you wouldn't actually add acid to acyl chloride, because unless you're behind some very, very heavy screen that will protect you, because it's not, it is so reactive. So you wouldn't even try it in acidic or basic solutions. The carboxylic acid, if I add the carboxylic acid to an acid, it sounds a bit silly, but if it's to a stronger acid, so I add this to say HCl, can you see that the OH can get attracted to the H plus from the added acid, and I've got water as a leaving group? And then depending on what I'm using in my base, it could either be OH minus or H2O as well. So I've left that as OH minus, but it could even be H2O again. And there is, of course, always a competing acid-base reaction, because remember, this is in basic solution, this is going to rather just deprotonate rather than substitute. What about an ester? An ester is very susceptible to acid and base. So if you think of polyester material, it's a polymer made from esters, and that's because when I have it in acidic solution, my OR protonates with the acid is an alcohol and neutral species. So would that be a good leaving group if it's neutral? Yes, so it's a neutral species, so it's a good leaving group, and that's why polyester, if you get spill acid on it, it's going to be affected. In basic solutions, it's also a neutral leaving group, and I will show you in the next slide, in case you're sort of wondering where does that H come from. I'll show you just now. And the same thing with the amide. In neutral solutions, doesn't really like reacting because it's got a very strong basic leaving group. But in acidic solution, it's only a slightly basic, weakly basic leaving group. So if that gets protonated, it forms ammonia, and ammonia is not too strongly basic, so it won't react that readily to go back on again. And in basic solutions, it's also ammonia, and I'll show you that now. So here it is where I'm trying to show you what's happening. My acyl chloride and water, the OH just adds on because I've got HCl coming off. The chloride is nice and neutral. The same thing with ammonia. Not that it would actually try, I mean, you actually do this reaction in conc ammonia, and you'll see that in another slide. But again, I've got a nice neutral chloride leaving group. I know you've got HCl, but the H comes from the NH3. Here I've got my ester. So just to show what happens in a acidic and basic solution. It doesn't do much in water. It doesn't really dissolve in water. So you need an acid or a base to make it react. In acidic solution, the OH from the water adds on. And can you see it's taken the H from the water to form a nice neutral alcohol? So I think that's quite straightforward. What happens in a base, the OH is a nucleophile and will add on, kick the methoxide off. But methoxide is very strongly basic. So remember, I've now formed an acidic carboxylic acid. So the methoxide's immediately going to grab that hydrogen and form ROH, and I'm left with the salt. So that's how, that's why it's also susceptible in base. Okay, so what you really have to learn with these derivatives and so on is form the acyl chloride, and that's always done by treating it with SOCl2 and then react further from that. So if I'm trying to make an ester or an amide, it's actually best to form the acyl chloride, and then it reacts very readily to form the others. So what I've got here, and hopefully something is going to appear over here somewhere, there it is. This is reacting my ethanol chloride, and I'm reacting it first with water, then I'm going to react it with ethanol, then ammonia, and then an amine, and so you'll see what happens in each case. So I'm going to just bring it through to 3.2 minutes. I wanted to do it in the beginning where you just sort of see, that's the acyl chloride. So I thought it was quite a nice, good image of what the acyl chloride looks like. And let's go to 3.2 minutes. This one has got a bit of mechanism that you will need at university level, but you don't need at level 3. So what they're going to be doing now is, okay, so they've got the acyl chloride, and did you see that bubbling when they added water? So, and you can see HCl is coming off because my conc ammonia in here is reacting with the gaseous HCl coming off and forming those white fumes. So I perhaps moved that on a bit too quickly. Let me react it now with ethanol, So it's just showing the mechanism there. 4 point. Okay, so here now they're adding ethanol. So all of these are containing ethanol chloride. And again, can you see how it's spitting? It's very reactive. So it's spitting out. Can you see all the fumes coming out? Those are all the HCl fumes. And because it's so exothermic, there's some steam coming out too, for any water that's in there. Now we'll react it with ammonia. And remember, we're getting to a better and better nucleophile being added, so it's getting more and more reactive. Okay, I'm going to move it on a bit more. So now they're adding ammonia. You can see the ammonia really fuming over there. And now have a good look at what happens here when he finally adds it. There. Right, you can see it's incredibly reactive. And did you see that white solid being formed? So remember what I said when we did physical properties? The amides are solids. So what we're forming here is an amide, and it immediately goes out as a solid. So they're quite distinctive that way. And if I do to the last one, I'm adding now a primary amine to the ethanol chloride. And if I just find my cursor always disappears. So, okay, right. So there is the primary amine, and it's now being added. And can you see you get that solid amide? It's now a secondary amide over there, but it forms straight away, and you can see all the fumes. It's the most reactive of the lot. So that's a good one to look at, but you don't need to know the different types of mechanisms. That's also shown there. This is one we've really shown, but you can see the thionyl chloride there, and it's really just reacting it now, not with an acyl chloride as we did last time. Now we're reacting it with concentrated ethanoic acid, so it's called glacial acetic acid. And if I just move it on, okay, there they're adding it, and you can see it takes a bit of time. It's not quite as reactive as ethanol chloride, but can you see there are those fumes coming off? So you are forming HCl. So this is the way you would go whenever you want to do a reaction. Take your ethanoic acid, form the acyl chloride, and then use that to react further to form an ester or an amide. And now he's just showing the different tests for it. So he's showing we've formed the ethanol chloride. You can see it bubbling away there. And he's also showing that SO2 is being given off because it's decolorizing permanganate. The SO2 is reducing the permanganate. When it finally gets there, you'll see the color change. So you can see the color changes quite readily. Okay, this is obviously done in a fume covered. You don't want SO2 gas and HCl gas around. Okay, so very quickly, let's see how much you remember. If I want to form esters, what reagent would I use? And these are mainly from either carboxylic acid or the acyl chloride. I would use, for an ester, yes, I would use an acid, but what I'm trying to ask, and I didn't ask it clearly, it's the reagents. Because to form an ester, if we're starting with either the acyl chloride or the carboxylic acid, I would need the alcohol. If I just did the acyl chloride, I would not need the conch sulfuric acid, because you saw what happened. It just bubbled away like anything. If I had a carboxylic acid, I would need this as a dehydrating agent to make the reaction go. So this is esters from carboxylic acids, otherwise just ROH if we're having an acyl chloride. If I want to form an amide, I just simply use conch ammonia in either case. Obviously, formation of acyl chloride is from a carboxylic acid, and I just added that SOCl2 as you saw in the previous video. And of course, to form a salt, I react it with any base. Because an acid is acidic, I react it with any base to form its salt. And then I've said over here, why is it better to convert the carboxylic acid to the acyl chloride first before making an amide or ester? And I hope you can answer it, is that it's pretty much, this is the most reactive. So yes, it's more reactive. So once you've made that, I don't need those extras like conc sulfuric acid or extra heating or just to try and drive it forward. This will just go zoom to form the ester or zoom to form the amide without a problem. Okay, you saw how it really, just reacted incredibly quickly to form that white solid with all those fumes coming off all over the place. Right, so now we've looked at all the reactions, and the last bit we're going to be doing now is polymers, and then the reaction schemes where we tie all those reactions together. Now, last year you did addition polymers, where we took alkene units and we linked the alkene units together. Okay, where the alkene bond broke and we used those electrons to link them on. This year you do condensation polymers, so it's a type of, not addition, it's a type of substitution, where we're removing, say, an OH or an amide or something like that, and we're adding something else on. And when we add these monomers together to make the polymer, we lose a small molecule. So if we're using carboxylic acid, we're going to be using water, because that losing water because of that OH coming off plus the H from elsewhere, or it might be HCl if we're using the acyl chloride, or it could be ammonia if we're using an amide, anything like that if we're bonding them together. Okay, amides, because they're not very reactive, we don't tend to bond those together. It's more the carboxylic acid or the acyl chloride. Now we can either form an ester chain, so COOC, or we can form an amide chain. So let's look at the ester chain. Can you see what we're forming here is that COO and then C. So can you see I'm repeating this unit, RC double bond OO, RC double bond OO, RC double bond OO. So that is our repeating unit, and we forming an ester link. There, I've shown it. Or it could be an amide. This is used very much in your proteins, your DNA. In fact, a lot of your body system is based on the amide chain. So if you're going to be doing biomedical or anything in that line, you'll certainly be looking at this. Right, the peptide bonds, quite correct. And they refer to that as well in the exam. So I've highlighted them in green, but if you see a C double bond O N, C double bond O N, you've formed an amide chain, and you can see the repeating unit is R, C double bond O N, and so on. But the important thing here is want to look at the ester link or the peptide link, because that's, whenever you get a polymer, is what you look for straight away. So here's an ester one. Now we can form it in two different ways. We can take a diacid or diacyl chloride, either of those. That gives us the carbonyl part, the C double bond O. And then we can use a diol to match up, and that gives us that O. Just remember we said it was C double bond O O. The C double bond O comes from there, and the O comes from the diol. Or we could use something that we call a hydroxy acid, where the reaction, the molecule has in the same molecule both the OH as well as the carboxylic acid group. So let's look at an example here. Here's a diol, di because it's got two of them, so diol, two OHs, and this is my diacid. If those were chlorides, it would be a diacyl chloride. And if I treat it with conc sulfuric acid, because remember that's my dehydrating agent, I'm going to be removing the H from the OH, and I'll be removing the OH from the carboxyl group. So can you see I've got two monomers being added together, the red one from the diol and the olivey green one from the carboxylic acid. Now have a look at the way this linking works. Can you see it's O, C double bond O, C double bond O, O. They are opposites. Oh, that's just to say we're removing water because of the consulfuric acid. And there are my ester links. And look at the order to see if you've got the first case or the second case, diacetyl or the hydroxy acid. So if I break that ester link, you can see my monomers. And can you see if I've got OCO, C double bond OO, OCO, C double bond O, they're alternating. I hope that's sort of clear that they're alternating. That means we've got the first case, diacid with diol. In the second case, a hydroxy acid. So here I've got a molecule with a carboxylic acid group and an OH. And I use my consulfuric acid because I'm removing water, that OH with that hydrogen. Now have a look here. If I sort of break it up, then can you see first of all I have C double bond OO, C double bond OO, C double bond, not Q. So it's not alternating, it's all the same. That means I've used a hydroxy acid. Because you might be given a polymer and be asked to write the monomers, and then in that case you've got to work out, do I have a diol with a diacid or do I have a hydroxy acid as my monomer, so you can write it down. Okay, the easiest way is just simply to break that ester link and then just write down the molecule in between. And remember, with the carboxylic acid, the carbonyl, just add an OH to it, because that's what was lost when we made the polymer in the first place. Okay, the amide polymers are exactly the same way. I can make it between a diacid and a diamine instead of a diol. Or I can use an amino acid. That's a molecule with a carboxylic group and an amine. So it's exactly the same. I'm now removing HCl. And if I look at my peptide link, okay, can you see if I break it up, I've got, so there's my diamine coming in, there's my diacid or diacyl chloride, there's my diamine, diacyl chloride. And it's the same thing if it goes NCO, CON, NCO, CON. If it's alternating, you've got this first case. If I've got an amino acid, so it's called an amino acid, I think it's quite obvious now because it's got an acid functional group as well as an amine functional group. And I'm losing the now I'm losing H2O because I haven't used an acyl chloride. I'm now using a OH. And can you see there's my peptide link? But if I break it, I've got CON. So it's all the same. Con. It's not alternating. So that means I've got an amino acid being bonded together. Any questions? Because I know this is a lot to take in. No. Okay. I really suggest when you're like answering the exams or answering the activities in the booklets, draw on the structures, circle the peptide links or the ester links, draw a line between them. Remember to always add an OH to the carbonyl when you're trying to make the monomer, and then it's much easier. Okay, this is just a video which is quite fun. If I was in a school and I was teaching you in the classroom, I would definitely be doing this. I'm just going to take it on a little bit. He's just doing the whole thing from the beginning, but I'm going to just do it from... Okay. What he's done, I'll go a little bit back a bit. Sorry, more back. He's dissolved the chloride in hexane, so it's not showing here yet. He's running it down here. Can you see it's running down the glass rod and it's coming on the surface? Hexane is lighter than water, less dense than water. And the diamine, of course, is soluble in water, being hydrogen bonding. And just think of, why did the silvical chloride, why was it dissolved in hexane? What would it do if it was added to water? So now on that interface between them, because the acyl chloride is so reactive, you can just pull out the nylon being formed. Okay, so remember, diamine, very soluble in water. You don't want to put an acyl chloride into water, so you dissolve it in hexane first. And if you just add it directly, you would get a real mess. Okay, this is now when we're going to be bonding two amino acids together. Now, this can be a bit more tricky because I've got a carboxyl group here that can react with this amine over here, but I've also got this carboxyl group here which can react with that amine over there. So your enzymes in your body does all this. That's what your DNA and your RNA does. It's your whole cells have got a way of connecting all these amino acids together in the right chain. In a laboratory, there's multiple ways it could happen. So if I've got two of them, there's at least two ways it can combine if I've got one carboxylic acid and one amine in each case. So here I'm going to react the alanine, which is one amino acid, with cysteine, which is another one. And if I take the NH2 of the alanine with the carboxylic acid of the cysteine, just draw this part out again and the carbonyl, and then just add on the NH2. So I've tried to color code it to make it clearer. So there's the CCC from the cysteine. Now I've added the NH2. Now that blue NH2 is attached to a red carbon, which is a CH. So there it is. And that red CH is bonded to two things, the carboxyl group and the green methyl group. So make sure that those are connected. So this, you've just got to be careful that you don't make careless errors. It's actually very easy as long as you are clear in what is connected to what. Then I can also take my alanine and cysteine, and I've now color coded this one, where I take my amine from the cysteine and I react it with a carboxyl group of the alanine. And so can you see I've now drawn this bit? So there's my blue carbonyl. And now I've added the pink NH2, and that is attached to a pink carbon. And that pink carbon is attached to a yellow carboxyl and this brownie CSH. So you've just got to make sure you draw it correctly. So those are the two things they ask you. They either give you the polymer and ask you to make the monomers, or they'll give you two monomers and ask you to make the polymer. And remember, you can link them in those different ways. The final thing that I haven't actually put on here that they can ask you is they can say, okay, if I have this chain and I want to break it up, what happens in basic conditions and what happens in acidic conditions? And that's when you've got to go back to my previous slide when I was doing it in acid and base. Because in basic conditions, if I get the amine back again, well, it's an amine here, and then if I get that amine back again, amine is a base. Is it going to react with a base? No. So my NH2 will stay NH2, no change once I've added that in. But now this one, oops, if I get my carboxyl group back here again, okay, if I have a carboxylic acid there, carboxylic acid is an acid from the name. What is it going to react with a base? Yes. So when you're asked to draw the amino acids that makes this up, don't draw the carboxylic acid back again if you have to do it under basic conditions, because this acidic oh, sorry, I've lost it. This acidic H gets taken off in the basic conditions. So you must write this as C double bond O, O minus, because it's basic conditions. If I had to break this up under acidic conditions, so say I had my polymer and I was now treating it with acid to break it up. So again, I just cut it off at the peptide link. Okay, so make a carboxylic acid and an amine. Will my carboxylic acid react with an acid? No, because they're both acidic. But my amine, NH2, is a base. Will that react with an acid? Yes. So if I was breaking this up under acidic conditions, I'd just simply reverse the reaction and form these two again. The carboxylic acid would stay the same, but now my NH2s don't stay NH2 because they will get protonated. So you need to write this as NH3 plus. So just change the 2 to a 3 and add a positive on it. Change that 2 to a 3 and add a positive on the nitrogen. So that's, I forgot to do that extra step in the slide, so that's just what you've got to be aware of. Right. Oh, actually I think I did it because I realized I'd forgotten it. Oh, there it is. Okay, well now you can see it. So if I've got that, I break it up. So there you can see it quite clearly. Under acidic conditions, I add my OH to the carbonyl group, but my amine, which is basic, will react with my acid, and can you see I formed a salt? Okay, and then of course my other one, which is this one now, I've done the same thing. My carboxylic acid stays the same, but my amine will now also get protonated, and I form a salt. So that's tends to come up nearly every year, or every year in some form. If a basic condition, okay, again I look for my peptide link, draw a line, and that OH always adds on to the carboxyl group, the carbonyl group, so that's where that comes in. But of course, it added as an OH, but because I've got a basic solution, that basic solution will take the hydrogen off of that carboxyl group and make it a salt. So in each case, I'm getting salts being formed. And then, of course, that was this one, so now I've got to do that one. And can you see my amine stays an amine? So I've just added a proton to it. But my carboxyl group over here, which was C double bond OOH, now has had that hydrogen removed because it's under basic conditions. So polymers, they can ask you 3 types of questions. Give you the polymer, make the monomers out of it, identify it. Give you the monomers, make possible polymers. Or they could ask you the hydrolysis of polymers under acidic or basic conditions. So just make sure you practice those things. Now in the last, okay, this one's quite fun. I'll go a bit further. So it's just showing what happens to nylon. Nylon is a reaction, so they're adding concentrated sulfuric acid to this. So nylon is an amide polymer. So you can already see what's happening. As he adds it, then you can see how it's just breaking up because it can't combine. Notice the polystyrene head underneath is not reacting. Polystyrene is an addition polymer. The nylon is a condensation polymer. So those are both polymers, but they're different types. And if I carry on further, 5.20, so now they're adding acetone or propanone. And can you see how the polystyrene is now dissolving? Because both are, well, propanone is not particularly non-polar, but it's non-polar enough and it will dissolve in the acetone. Sorry, the polystyrene will dissolve in the acetone. But notice how the nylon is simply not affected at all. So different polymers, if it's an addition polymer or a condensation polymer, have got different properties. You learned about the addition ones last year. This year is the condensation ones. Okay, so some quick questions. Match the monomers with a polymer. So I've done the polymer in black at the top. A, B, or C? Which one is the correct answer? So in A, I've given you a hydroxy acid. So are we repeating it? Are we getting Q, Q, Q? Or are we getting alternating? So look for those ester links. And if we're getting alternating, is it B or C? It's alternating, so we know A is out. So it's either B or C. Actually, it's not B, it's C. Because do you notice with B, we've got a diol, but we've got a hydrox, we don't have a diacid. So we need a diol and a diacid. So, okay, there I'm just showing where it's breaking up. Okay, so it's diol diacid, so it must be C. So it was a bit of a trick question because you saw the diol there, but that's not a diacid. Okay, here's another one where now I'm going to say which one does not match the polymer. And I'll let me give you the reason why. Is because, remember, you could have an acyl chloride or a carboxylic acid. They both could be suitable. So which one? So first of all, you've got to see straight away where is the peptide links, okay, and are they alternating or not alternating? So here I'm just breaking them up. So is it going con, or in this case NCO, NCO, NCO? I mean, is it the same or is it alternating? It's the same. So we know that it won't be a diamine and a diacid, and I haven't given you that option, but say in the exam they could. But so now we've got to see what does it look like. So I've deliberately reversed it to make things a bit more difficult. There's the carbonyl, there's the carbonyl. So I've got CH2, CH3, and then NH. So that looks as though it could match there. And here it's got C, CH2, CH3, NH. That also matches. This, I've got an extra OH here, which muddies things up. It could actually also, the OH could also react and not just the amine. Remember, we could get some ester links as well. But, oh, hang on. I haven't been looking very carefully here. Oh, A matches and C matches. N is the one that doesn't match. I should have made that a red cross. Because can you see, this cannot form this polymer. Because if this NH if I reacted it with an OH, I would get a ester link and not a peptide link. Does that make sense? Okay, sorry, I made myself muddled by doing a negative, and I hate doing double negatives because I always get myself muddled. So why we can say B will not match this polymer is because that would make an ester link, because the OH would react with this carbonyl and kick out an NH2, so we wouldn't get peptide links. Right, now this one I got from the University of York site, and I've just blanked out, as you can see in these areas over here, the reactions that don't apply to your level 3, but it's a useful reaction scheme. You've also got a scheme on page 78 of your book. I really suggest you learn that, and you learn it in terms of also your substitution, addition, elimination, and so on. So make sure you know the different types of reactions. Here, this isn't color-coded. Well, they have color-coded it, actually, because that's also oxidation. Yep, they have color-coded it. But remember your alkenes, the different types of reactions. I've left in that addition polymer. You did it at level 2, but you don't do really at level 3. But otherwise, there are your 4 reactions. They've actually, I should have blanked this one out as well. You don't have to know this particular one over there. So actually, I should have blanked that one out. So there are your 4 reactions, and then you can see all this bit over here is what we did with the acyl chlorides, esters, carboxylic acids, and amides. When you look at the video, you could look at it in detail, or you could just Google it and get your own copy if you liked, or you might find this a lot simpler and just use the one given in the booklet. But try and learn these reactions as much as you can, because it's a lot to learn. Okay. Now, in the last 10 minutes, reaction schemes. Once you've learned all those reactions, you've got to be able to put them together in a scheme. So how do I get from A to D? You know, which pathway do I go? How do I get to B to C to get to D? So you need to know things by reactants. What reactions do alkenes undergo? What reactions do alcohols undergo? The way I've been doing it a bit now. But you also need to learn about product. So how could I form alcohols? I could form alcohols from alkenes. I could form alcohols from aldehydes. I can form alcohols from ketones. I can form alcohols from haloalkanes. So you need to know all, sort of going backwards to the product. Then also learn it by reagent. So where did we use SOCl2? So think of those sort of reactions, learning it in that way. Then learn your tests, because they'll sometimes give you information in a test. They say a test positive for tolerance. Then you know you've got an aldehyde. Or it decolorizes bromine. Then you know you've got an alkene. And then, of course, they'll talk about minor and major products. So you need to know Markovnikov and Zaitsev's rule. So this is from the 2013 exam, and it said basically complete the reaction scheme by drawing the structural formulae of B and C and include the necessary conditions. So if you read all the way through, the important thing right at the end is a base, because you're going, what on earth is over here? But if they tell you that compound C is a base, what functional group is the only functional group that is a base? An amine. So you know that compound C is an amine. And so that's immediately an information you know where to get to. Then you also know that an amine, how do I form an amine? I could form an amine by treating a haloalkane with ammonia, or a haloalkane with a primary amine. So the very fact that it says a primary amine over here means I'm forming a secondary amine over here, and I wouldn't be forming an amide, because an amide is not a basic. Because the only other place where you use a primary amine is, say, treating ethanol chloride with a primary amine to form an amide. But because an amide is not basic, you know you're not doing that. So you know that this is an haloalkane. Now we just put it in. If I've got 3 carbons in a row, then I need to get a product that's 3 carbons in a row, and an easy way of doing that is using SOCl2. You could say PCl5 or PCl3, but just learn SOCl2. It's much easier. So 3 carbons in a row, you form a primary haloalkane. Then I treat that with methanamine, and remember, it's a substitution reaction, so the chloride goes out, and I add the N on here. So can you see there's the N added onto that C, but of course the methyl of the methanamine is over there as well. So that's a very short reaction scheme that came up in the 2013 exam. Okay, here's what came up in last year's exam, and can you see they give you a lot of information, and there is your scheme, and you've got to get up to ester H. So you know A is oxidized to C, so the only thing you really oxidized were alkenes, alcohols, and aldehydes. Okay, and you start with an alkene, so you know that, well, you know it's an alcohol anyway. B is oxidized to form product D. So you already know if I'm going to be oxidizing an alcohol further, if it's a ketone, it's a dead end stop. So this will be a ketone. This will be the aldehyde. Because aldehydes, you can react further to form carboxylic acids and do all those other funny things. Okay, so let's, and then of course, when you've got major and minor products, as you've got over here, you must immediately think of Markovnikov and Zaitsev. Markovnikov if you're doing an addition. Okay, there we said it's a ketone because it's a dead end stop. Here, because we're reacting it, we could have oxidized it straight to the carboxylic acid, okay, or we could have stopped at the aldehyde point of view. But if product D was an aldehyde, do you know of a reaction of aldehyde with SOCl2? No. You only know your aldehyde is either being reduced with sodium borohydride or oxidized. So you know that product D is not the aldehyde. We've gone through all the way to the carboxylic acid, because now we're doing that, what we learned today, all those derivatives, swapping it around, making the acyl chloride and esters and so on and so forth. And what else do we know? Well, with SOCl2, we know this has to be acyl chloride, and if we're reacting it with ammonia, it has to be an amide. So we can really put those ideas down. So let's start. Propene, draw it out. You know what propene is. Now remember the major product by Markovnikov, the hydrogen adds to the carbon with the most number of hydrogens, so it'll add to the C1. Okay, so it's added there, the OH added there. The other one, anti-Markovnikov if you like, where it does the minor product is where the OH adds where the hydrogen should have added according to the Markovnikov rule. Now we're just adding this further, and so it's going to get oxidized to the carboxylic acid. The carboxylic acid now gets changed to the acyl chloride to form the amide, and here what we've done is we've formed the ester. So from the carboxylic acid, you've got to add alcohol B. So can you see what I've done? I've looked for the O, okay, and then I've seen, okay, I've got 1, 2, 3 carbons. So there's my CO, that from the alcohol. So everything in purple is from the alcohol, number B. And this one is this over here. There's my red O, it becomes my purple O down here. And I've got this carbon attached to 2 methyl groups. So my carbon attached to the O must be attached to 2 methyl groups. And that is the end of organic chemistry. Okay, so the really important bit over here is please learn your reactions in all those different ways, because you'll find then these schemes are really easy to do. Okay, you have a good day. Next week we're going to be starting with the spectroscopy. Right, bye.